Hi, everybody. Hope you're staying safe. Previously, we talked about the postulates of quantum mechanics. Let me show you here. Show it here. First one is that physical states must be represented in a Hilbert space. Second is that physical observables must be Hermitian matrices or operators, which means real eigenvalues. And there are still a few more postulates. We talked about the probabilistic interpretation due to the Copenhagen school. To be discussed, the time evolution. I can put it as a postulate, the Schrödinger equation, but we'll just explore a little bit more these first three postulates of quantum mechanics. So, to start with, I must ask you to demonstrate a little things with some objects known as Pauli matrices. Okay. Pauli matrices. There are three Pauli matrices, and they are related to spin half of particles. These three matrices usually are represented as a vector of matrices in the x, y, and z directions. And I will ask you to demonstrate the eigenvalues and eigenvectors. Eigenvalues you must show, okay? Show or demonstrate or find. So in exercise, find the eigenvalues of Pauli matrices. Second thing to do, find the eigenvectors. All the Pauli matrices have the same eigenvalues. So the eigenvalues are +1 and -1. Okay. The sigma Z matrix is already in the diagonal form. So it has the eigenvalues in the main diagonal. But the others, sigma X, for instance, is a non-diagonal matrix. So you'll find by the equation, okay, the determinant of the matrix minus the identity multiplied by the eigenvalues, lambda, say lambda, equal to 0, you'll find easily you'll find that the eigenvalues are +1 and -1. There are two eigenvalues, okay? So it is a Hermitian operator. This is also Hermitian. Sigma y is also Hermitian. And you'll find the eigenvectors, the eigenvalues to be real, +1, -1. All right. After that, you can find the eigenvectors to be, this is the answer, vectors. I'll put the eigenvectors of sigma z. It's a complete basis. The plus state or the up, you can choose the convention or the minus or down state. They are represented this way. Okay, so you can uh, find out that for sigma x, using the basis that diagonalize sigma z, the eigenvalues plus in the x direction corresponds to 1 over the square root of 2 plus state plus the minus state, which means if you write it as a column vector, 1 over the square root of 2, 1, 1. Okay? This is related to the plus eigenvalue, the plus 1 eigenvalue of sigma x. You'll find that. All right? And if you choose the minus, you pick up the minus eigenvalue, you'll find this eigenvector up minus the down state, or plus minus the down state. All right, and if you write it as a column vector, you'll find that it is a 1 minus 1. You'll find this one, this thing. It is to be normalized because if you project this state onto itself, it must give you the unity because it has a probabilistic interpretation. Okay, so you must work eigenvectors and eigenvalues of matrices. It's important mathematically. You need to work these things out, right? Well, also you can write a matrix if you define a unit vector this way. Cosine of theta, cosine of phi, a cosine of theta, the sine of phi, and the cosine, and the, excuse me, unit vector, define it this way, better this way. Sine of theta, cosine of phi, sine of theta, sine of phi, and cosine of theta. This is the vector. I hope it's clear what I just wrote. You can define a matrix sigma. It's a vector of Pauli matrices dot. It's a scalar product in the sense of real three-dimensional space, and this corresponds to sigma of x. This thing here, I'll call it nx, plus sigma y and y, which is this thing here, plus sigma z and z, which is the cosinus of theta. And this is a matrix, has the following form: nx, no, and z, and x minus I and y, and x plus I and y, and minus z. You can find it. It has a unit determinant because it has this form here. So if you calculate the determinant, you'll find 1. You'll find negative 1. In reality, negative 1. This is a Hermitian matrix. You can demonstrate that. Okay, you can demonstrate this thing. Notice that n dot n is equal to unity. It's easy to demonstrate that because of trigonometric relations between sine and cosine. So you can find it. right? Define this matrix here and find eigenvalues and eigenvectors. You'll find +1, -1, and the eigenvectors, okay? Define this thing and find eigenvalues and eigenvectors for sigma dot n. You must find that. In the book of Sakurai here, you can make you can make a reading of the chapter 1 of this book and solve for the exercises, the problems. I guess you can see here the problems in chapter 1. So there are few related problems. Uh, they have to do with the Pauli matrices. So solve that. Okay. Well, also demonstrate for Pauli matrices the following. I need to define commutators and anti-commutators, but I'll put it here as an exercise in, and we'll talk about commutators later. Sigma of I can be X, Y, and Z here, right? Sigma j, the commutator, which means you must perform the matrix product in this order, this first and this second, minus, reverse the order, you find it to be twice the imaginary unit. It's not this, this I is just an index, and this I is the imaginary unit, okay? The sigma of k, and this is the Levi-Civita tensor, or symbol, to be precise, okay? So if you pick sigma x here and sigma y here, you'll find out that the commutator of the product, you can do it by explicit calculation, matrix product, sigma of x, sigma of y, minus sigma of y, sigma of x. You show that this is twice the imaginary unit, sigma z. And if you perform cyclic uh, changes here, permutations of the symbols, you can put z here, x here, and y there, and cyclic changes. So if you change here, you can perform put the x there, the, the z here, and right. And if you keep the y here, you have a minus sign here. All right. That's encoded in the Levi-Civita permutation symbol. All right. As a matter of fact, you can put the y there, the x here, and the z here, and you'll find the relation, which means sigma of y commutated with uh, sorry, sigma of z commutated with sigma x is equal to twice sigma y, right? You can make permutations, cyclic permutations, x, y, and z. This is the cycle, and you'll find all the relations encoded by this symbolic equation here. But you can demonstrate at first this one. Sigma x commutated with sigma y, it's twice the imaginary unit sigma z, all right? Also, it's important, the anti-commutator of two of the Pauli matrices is equal to twice the Kronecker delta of I and J times the identity matrix, a 2 by 2 identity matrix, okay? Because these are 2 by 2 matrices. And for instance, if you pick, this anti-commutator corresponds to sigma of y, sigma of j, plus the product in the reverse order. So you must show this thing here, right? It's not too much difficult to perform the calculations, right? So if you choose a sigma x anti-commutated with itself, it gives you twice the identity matrix because you are choosing I equals to j. But if you choose x and y here in the anti-commutator, you'll obtain a vanishing result, a zero, a matrix of zeros, okay? That's it. So you must demonstrate these things. Why Pauli matrices are so important? Because they are related to spin half. Pauli matrices, we'll talk about that more later, but spin half, right? Rotations, a representation of rotations, and it has to do with spin half particles. So let us explore a little bit the consequences of the non-commutativity of Pauli matrices and in general for many other physical observables, okay? So it's very, very important. I recommend you do that, all right? Well, with respect to the physical observables, the operators, representing physical observables, they are represented by matrices, which are Hermitian, and you can calculate for two arbitrary physical observables for A and B operators. It can be position, momentum, spin in the Z direction and the X direction or whatever. Okay. You can calculate a thing called a commutator, right? You can calculate this object here. The matrix product in this order, A times B minus B times A, right? And this is called a commutator, right? And this symbol here, I hope I can do it right so you can see exactly this is one form of a bracket and this is a curly bracket, okay? So the symbol means that this bracket means commutator and the curly bracket, all right, is the anti-commutator. You can perform a product of two matrices or two operators and sum the product in the reverse order. Okay, this is the anti-commutator. Right? So we'll do that for Pauli matrices, the commutators of all the Pauli matrices, and the anti-commutators for all the Pauli matrices. All right? And it's a very important thing to calculate for two physical observables, A and B, position and momentum, spin in one direction and the spin in another direction, or whatever you want to calculate here. It's very important to have knowledge about the commutativity of the operators or non-commutativity of operators. The anti-commutator, it's very important also, but we will see the importance a little bit later. Okay, it's related to statistics. Well, so this is the operation which matters for now, the commutator of two physical observables, right? Okay, and well, I didn't commented about the Levi-Civita, which I wrote previously, Levi-Civita symbol. This symbol means a plus one, a minus one, or zero. If you have I, J, K in a cycle 1, 2, 3, or you can just move the 1 to the end, so you get 2, 3, 1, right? The 2 goes here and the 3 goes here, or any sequence do you want, or if you prefer, you can write a sequence 1, 2, 3, 1, 2, 3, dot here. The cycle goes forever. 1, 2, 3, or 2, 3, 1, or 3, 1, 2, or again 1, 2, 3. This cycle, if you plug in here 1, 2, 3, or 2, 3, 1, or 3, 1, 2, you'll get a plus 1. It's a commutation, a permutation of indexes. But if you choose AJK equals to, you permutate two of them here, 2, 1, 3, and then you can repeat 2, 1, 3. If you choose I equals to 2, J equals to 1, and K equals to 3, or 1, 3, 2, or 3, 2, 1, you'll get a minus 1. And if you repeat any index, I equals to J, for instance, 1, 1, or if you plug in J equals to K, or if you plug in I equals to K, it gives you 0, all right? So you must have the three indexes distinct from each other. If you repeat, 0, okay? And the cycle 1, 2, 3 may be 1, 2, 3 if you are talking about coordinates in space are x, y, and z. But if you're talking about just permutations of any other kind of symbols, I don't know, right? So in the rectangular coordinates, 1, 2, 3 means x, y, z, right? This is the right-handed convention, right? So this is the Levi-Civita symbol, right? But let's go back to the commutation of operators. So you see, Pauli matrices do not commute. Pauli matrices do not commute, all right? And I am anticipating that the Pauli matrices are related to the spin of spin half particles, such as electrons or protons or neutrinos or whatever spin half particles you are interested in. So what the relation means is that you cannot measure spin in one direction without affecting a second measurement in another direction. And for in general, for two operators, A and B, if they are commuting operators, if the commutator of two operators gives you a zero, it means A and B commute, right? They commute with each other. So, in this case, if two matrices commute, they can be diagonalized, which means put in a diagonal form all the eigenvalues in the main diagonal and all the other entries zeros, all right? If they commute, if two operators commute, they are represented by matrices, which can be diagonalized by the same basis. In Hilbert space, we are talking about quantum mechanics here, so in Hilbert space, the basis which puts A in the diagonal form puts B in diagonal form, right? This is very important. But if you have A and B distinct from zero, the result is the non-vanishing matrix. The observables A and B are said to be incompatible, right? Incompatible. If you have zero, they are said to be compatible, right? If this is the case, compatible. If this is the case, incompatible, or non-commuting operators also, you can say. And in the second case, if you have two non-commuting operators or incompatible operators, they cannot be put in diagonal form by the same basis. If you choose the basis, the eigenvectors of A will be diagonal. It will be represented by a diagonal matrix. But B will have numbers, will have values outside the main diagonal, right? And of course, if you choose the eigenvectors, which means the basis, so that B is diagonal, then A is non-diagonal. You cannot diagonalize both simultaneously by the same basis. All right? They do not, A and B, do not share the same basis. All right? This is a very important result. Okay? But what that does really mean for physical operators? So we have two kinds of operators: compatible and incompatible, right? You can think about a measurement. There is the collapse of wave function and all that, but the measurement corresponds to the application of an operator to your system. So if you measure a two operators, consider two operators A and B, position and momentum or whatever do you want. Okay, spin x, sigma of x, sigma of z, or sigma of y, sigma of z, doesn't matter. All right. If you choose two operators and you measure first the operator B and then the operator A, you are performing an operation on the physical state of the system, right? And you read it this way. First, B acts on the physical state, and then A acts on physical state. This is the physical state of your system. And these are the operations in a measurement, for instance. So B acts first, and then acts the operator A. You must read the equation from right to left, okay? This first, B first, and A second. This corresponds to measuring B first and then A. This is the operation AB, operating on the physical state of the system, the cat representing the initial state of the system, or a given state of the system, all right? So this representation means B acts on psi, and then A acts on the result, on the resulting state. Because when B acts over the state psi, you'll have another state phi. So A acts on the new state, right? But and this means you are measuring B first and then A. This is the order of measurements. First B and then A, right? But you can measure in the reverse order also. So to pick up a definite a particular example here, consider B to be sigma z and A to be sigma of x. You are measuring the spin in the z direction, and after that, you are measuring the spin in the x direction. All right, this is the order you are doing the operation. But you can measure the spin in the x axis first and then the z axis. You can reverse the order of measurements. All right, so you can perform a measurement of A first and then B, operating on the physical state of your system. So this first and this second, right? First A act, which is closer to the state, and then the other, okay? You need to perform this operation, and then, well, matrix operations are associative, but you cannot change the order here. So physical interpretation is you are measuring first A and then B. Measuring, operating, or acting A on psi first, and then B on the resulting state. Right? If A operates on one of its eigenvectors, you get an eigenvalue. And B will operate on an eigenvector of A, but perhaps an eigenvector of A is not an eigenvector of B. So, and for the other case, the same applies, right? same lines of reasoning applies. All right. So order of measurements or measurement order is important in quantum mechanics because you can have distinct results from measuring in one order or the other way, the reverse order. All right. In classical physics, in classical mechanics, you can measure position and then measure velocity of a particle, and it doesn't matter because you can measure first the velocity and then the position. The result is the same in classical physics. But in quantum mechanics, that is not guaranteed. Why is that? Because if you make a B measurement and then A measurement on the state side, or you measure first A and then B in the same prepared state at first, these things may be distinct. It may be, perhaps it's not when these things commute. If the matrices commute, it doesn't matter. You can do the measurement of A and then B or in the reverse order. But in general, they may not be equal. So what is the thing you use to obtain that information? You can calculate what is the result of measuring this order or in the reverse order, and you'll find what it gives, right? But matrix algebra, you can put the state here in evidencing the state, and you can put the operation of measuring B and then A minus measuring A first and then B here in front of the state. And it can be applied to any arbitrary state. So you drop this because it's arbitrary, and you really need to evaluate AB minus BA. So this thing is the commutator. You need to know what is the result of a commutator of two operators to have knowledge about the compatibility of these operators. They can be compatible. If you can change the order, they are compatible. You can measure A and you can measure B in any order you want. But if they are non-compatible, the order will influence the final result of our measurement on the system, on a physical system. So you have two possibilities here. It is equal to zero or it is distinct from zero. Then, in this case, compatible, and in this case, incompatible. When two operators are incompatible, you destroy all the information when you measure. I must explain a little bit more about this. When two incompatible, consider two incompatible observables, right? If you measure B first and then A, the result will be different from measuring A first and then B, right? This is the order. So this is the commutator. It is distinct from zero. And when you measure first B and then measure A, when you do that, all the information you got previously by measuring B will be lost when you measure A. So, if you measure B first measure B, get some result of the measurement, right? Get some result. And second measure A. If they are incompatible when you apply the second operator, you will destroy the information you get from the first measurement. All right? It is destructive because anytime you measure, your state goes to an eigenstate of that operator. Okay? So this is a hat here representing an operator. Okay? It's not a unit vector. So if you measure first B, the state will collapse to an eigenstate, an eigenvalue of B, right? But this eigenstate of B is not an eigenstate of A because they are not compatible. And I will not show that. I guess there are mathematical demonstrations you can find elsewhere. But when two matrices, two observables are non-commuting or incompatible from the physical point of view, the commutator is distinct from zero, you cannot have the same eigenvectors for both matrices, for both physical observables. The eigenstates are not the same, right? And in this case, when you measure B, a measurement always show an eigenvalue and the system collapses to that eigenstate. So when you measure B, your system goes to an eigenstate of B. But then this is your state, an eigenstate of B. If you measure A, the system will collapse now to an eigenstate of A, which is no longer an eigenstate of B. So you destroyed that information. That information no longer exists, right? The system collapses to an eigenstate of what you are measuring. So if you measure in the reverse order, if you do measurements of A first and then B, in the reverse order, first you will have an eigenstate of A, and then you will have an eigenstate of B with its eigenvalues, right? So this is very, very important. In quantum mechanics, the order of operation, the order of measurement matters. It is important. You cannot neglect that fact, right? So you can find general uncertainty relations. We'll finish this class, this lecture, better said the lecture, with an exercise. I hope to do that, right? But first, uncertainty relations. In many situations, many textbooks, it is discussed as eventually as it has a status of a postulate, all right? It's the uncertainty principle or the uncertainty relations. But it's just the fact, it's just a consequence, it's just a corollary of physical observables being represented in quantum mechanics by Hermitian matrices. So it's a consequence of physical observables being represented by operators. They can be differential operators or matrices, but even a differential operator can be shown that it's just a limit of a matrix. So matrices, you need matrices to represent. In classical physics, energy is just energy. It's a number. At a given instant of time, a particle has an energy. In quantum mechanics, the energy is an eigenvalue of a matrix, the Hamiltonian, which is a matrix. It's a mathematical operator, all right? So the matrix representing the Hamiltonian has eigenvalues, and what you can measure are the eigenvalues of this matrix, all right? In classical physics, this is just a function of, eventually a function of time, right? The energy is a function, or just a number in a continuum of values, right? In quantum mechanics, physical observables, energy, momentum, position must be represented by, in the end, by matrices, right? So the uncertainty relations are a consequence of matrices being used to represent observables. But let's just uh, calculate or demonstrate the uncertainty relations. So you need first to consider averages. You need to consider average of operators. Okay, if you have two operators A and B, the average of A given a physical state psi, it is just this thing here. This is the average of A. Given the physical state, you can apply A to psi and then apply a bra here. This is the average of that operator. It's the average of A given the state psi. All right. You could put a psi here just to remember that's the average considering a cat state being given at a given instant of time. Also, the average of B considering psi given is just the projection of the result of a measurement of B in the direction of the given state, psi. So you just put in the middle of your sandwich, which has, say, a cat here, a bra here, you just insert here the operator you're being interested in measuring averages, and this defines averages. All right. There are other kinds of measurements or averages related to density matrix. We'll talk about density matrix a little bit later. And the average is a little bit differently, it's defined differently. But consider the average to be given by such an equation. The average of A is just the projection of a result A applied to psi over psi. Right? This is the average of an operator. Right? If you have, for instance, the Hamiltonian, which is related to energy, and you give a state of superposition, you can find the average energy, of the system. I put a bar over here. It's just given psi, just do the math here. You multiply the Hamiltonian by the state which you prepared at first, and then you project again with psi, you have the average of energy measurements. But it's important, single measurement always, it's very important in quantum mechanics, always produce an eigenvalue of the operator being measured. So if you want to know in the real world how to obtain this average, you need to prepare an ensemble, an infinite set of systems equally prepared, and you measure independently each one of them, and you tabulate, you create a table of values, and then you can average the values you obtain. So if you prepare a state of an hydrogen atom as, say, 1 over the square root of 2, the 1s orbital, you put electron in the fundamental state, but also you can put a combination of an electron in the px orbital, the orbital p, in the second electronic layer. Uh, when you measure energy, you'll find the fundamental energy of the hydrogen atom or the energy of the second layer, the n, the principal quantum number n equals to 2. And a single measurement, 50-50 chance in this state, you'll find or the energy of the fundamental state or the energy of an excited state. Just that. So you need to prepare many hydrogen atoms with this state here and measure independently all of them. And only that way you will find that your measurement gives a 50% chance of being in the fundamental state and 50% chance of being in the excited states, and the average of the energy you measured will be, in this case, for this state, will be 1/2 the energy of the fundamental state, the state of n equals to 1, and 1/2 the energy of the second state with n equals to 2. Okay, in this scenario here. All right. But a single measurement, if you pick one of the hydrogen atoms and measure that one, it is in this state, and you apply the Hamiltonian. The atomic orbitals are eigenstates of the Hamiltonian. All right. You'll get as a result an eigenvalue, or E1 if you by chance measure this state, or E2 if by chance you measure that state. So a single measurement, say you measure the fundamental state of that hydrogen atom, you'll be measuring this particular value. In the case of hydrogen is minus 13.6 electrovolts. And second, I don't remember exactly the value, but you can find elsewhere. So if you measure a single time, you will find this value or the other value, And if you measure and measure and measure over a collection of hydrogen atoms prepared in the same way, you will find an average. And the average is given by this equation of the energy, but it would be any other operator you would be interested in measuring the spin of the electron. So you can average the spins. You measure spins, and then you have the average of the spins. The averages can produce values in a continuum, all right? But a single measurement in quantum mechanics will produce an eigenvalue of the operator, always an eigenvalue of the operator. So I may say, suppose the average, it's a discussion of a real problem here. Suppose the average of energy measurements of hydrogen atoms, the average of measuring hydrogen atoms prepared same quantum mechanical state, each of them is, say, minus 10 electron volts, right? Suppose that. What do you expect from a single measurement? What do you expect to obtain for a single measurement? If world would be a classical world, you would be confident in saying, okay, I guess I will find minus 10 electron volts. But that's the incorrect answer. What do you expect from measuring performing a single measurement? You must expect an eigenvalue of the Hamiltonian. And you can put a list of values: minus 13.6 electron volts, the second orbital, I don't remember exactly the value, the third, and so on. It's given by a formula. If you neglect spin and other interactions, it is minus 13.6 electron volts divided by the principal quantum number squared. So this is the 1s orbital, it's 1 here, minus 13.6 electron volts. If you plug in the second orbital, you find minus 13.6 divided by 4. So it's around 3.5 electron volts, something like that, right? So a single measurement will give you an eigenvalue. That's what you must expect from a quantum measurement, right? It's very important. But after you measure a lot of times the same system prepared in the same, it's not the same hydrogen atom. You must prepare a sequence of hydrogen atoms with the same state at first, and you measure independently all of them. And in that way, you can expect an average, right? All right. Um, let's go back to the uncertainty principle. So if you are dealing with averages, you can also calculate the standard deviations from measurements, and this is determined in statistics by this thing. Usually you define, okay, define this operator delta of A. This is the operator A minus the average of A, the average with respect to that state psi. I will not write down here just to make the notation clear, a little bit clean, perhaps is better said, clean, clear. I would put psi here, but just make things more complicated, perhaps. Define this thing. So you can square this object and you'll find the operator squared. An average is just a number multiplied by identity matrix. We usually do not write an identity matrix just to keep the notation a little bit simpler. It's clean here. Do not write it. Do not write the identity matrix. So if you square this operator, you have a squared minus twice a, the average of a, plus the average of a squared. And this is the delta of a squared. And this is an operator which is related to the variance. All right? Variance is defined, statistically speaking, for matrices given a state vector, which is the state psi, is defined by this operation here. All right? So if you take the average of this, you'll have the average of the squared operator minus twice the average squared, and the average of an average, the average, it's already squared. So you can find that taking the average of delta A squared, this operator squared, you will find it is the average of the square minus the average squared. All right, this is distinct from that. Okay, here you pick the squared operator and you take the average, and here you pick the average of the operator and you square that number. All right, always this thing here is greater than the previous one here, so the average of the square is always greater or at least equal to the square of the average. All right, this is a very important result in statistics, and in quantum mechanics we are dealing with probabilistic interpretations. Right, so you can define that for an operator B also, delta of B squared, it's the same thing, but for an operator B. Okay, and now we can use a identity which is due to Schwarz and Cauchy. And there is another guy, I don't remember the name. It's Schwarz-Cauchy or Cauchy-Schwarz inequality. And this inequality is related to scalar products. Here it's better to work with scalar products. Say you have an alpha vector, you project it to itself, and you can pick a beta vector, project to itself. In quantum mechanics, this will give you one, the unity. So in quantum mechanics, one, but in general, in Hilbert spaces, vectors are not necessarily normalized. So I can put modulus here. So this modulus multiplied by this modulus is always greater or at least equal. This is always greater or at least equal to the projection of alpha over beta modulus squared. It is simple to understand if you pick up two vectors. Okay, you can put real vectors also. It's valid for complex vectors, but you can pick real vectors. If you pick real vectors, suppose this is they can have the same length or size, because in quantum mechanics all vectors are normalized to unity, but it's not really necessary. So this is alpha and this is beta. And the projection of beta over itself is maximized because beta is in the same direction of itself, and also for alpha. Okay? But if alpha and beta forms an angle, it's a complex vectors, more difficult to see that. But consider real vectors for the sake of simplicity. Inequality is valid for complex vectors also. So if you put an angle theta between these two objects, of course the projection of this into that will be less than the projection of a vector with itself and the other projection and the projection of the other vector with itself. So the squared value here of the projection of one vector into the other, the squared value of that, is always less or at maximum equal to the projection of vectors with themselves. All right? This is very important, Schwarz inequality. So I can consider this thing here. Suppose delta of A, the operator, is A minus the average of A. Given psi. The physical state is arbitrary. You can choose whatever you want. And delta of B is B minus the average of B. Okay, this is related to when you square this operator and you take the average, this corresponds exactly to the variance of that operator, okay, of A, suppose, the variance of A. You calculate that way. Given the physical state, it's delta of A squared and projected onto psi. So I can define the vector alpha to be delta of A multiplying psi. I can define beta to be delta of B multiplying psi, the physical state. And we can plug these things onto Schwarz inequality. All right? Alpha is this, beta is that, okay? And you can calculate the variance, all right? Because look look at this thing. Alpha projected to alpha is equal to psi, the transpose conjugate of this operator. So I'm writing the alpha here, and I'm writing the bra of alpha here, right? But remember, A is Hermitian because we are interested in physical observables related to this equation. So it's general here, but we are interested in Hermitian operators. So also delta of A is Hermitian because it only enters A inside of that operation. So we'll find here this is exactly the variance, okay, which we write simply as this thing here. And the same we can do for B. So we will have the average of delta of A squared multiplying, notice this is alpha, multiplied by alpha, modulus. I can pick the modulus, but it's positive because, as I said, the average of the square is always greater than the square of the average. So this is positive, don't need the modulus here, but okay, you can put modulus here. This is positive definite already. And you can do the same for B, all right? If you pick beta, define it by delta B over psi, the same state, given state. So this is always greater, at least equal to, say, I can put the alpha here and the beta there. It's just the average of delta A, delta B. All right? Modulus. Here I need modulus. And this is squared because vector squared. So this corresponds to the beta projected to alpha. It doesn't matter the order. Okay. So this is the projections, Schwarz inequality. And this thing here, you can write any matrix product, whatever do you want, A and B multiply this order, you can always write it as AB is equal always to the half of the commutator plus half the anti-commutator of these two objects. Okay, it's always true to write. And also for delta V, delta V and delta V, they are two matrices. It's half delta V, delta V, plus 1/2 delta A, delta V. But you can demonstrate that because in delta of A you have an operator minus the identity matrix multiplied by a constant, which is the average of A. And the identity always commute with any other matrix, right? Identity always commute with any given matrix. It can be here B or another O, or just another matrix or another operator, and this always produce 0, right? So here you'll find that the commutator of A with the average of B and the average of A with B always gives 0, and the average also commute because they are numbers multiplying the identity matrix. So this is in fact the commutator of A and B. Oh, the commutator, this thing measure if two operators are compatible or incompatible, okay? And that is just the anti-commutator of two matrices. But it's a stronger version, perhaps. They say there's the strong version and the weak version of the uncertainty principle. You always drop out the term. It's to be precise, it's mathematically incorrect, but it doesn't change the inequality. As a matter of fact, it makes it stronger to let that out, and you find this thing here. The variance of an operator A given the state psi multiplying the variance of the operator B is always greater or at least equal to 1/4 the modulus of A commutated to B, taking the average of the thing, to be precise, because we have the average in the previous board. I had written without the average, but you need to have average here. So squared, all right. And there is a thing called standard deviation. Many textbooks use for delta of a number, not an operator. We are using here operator, just like in Sakurai, but there are books which use this thing as operator, as a number. Okay, so standard deviation, say sigma of A. It's bad notation because you can confuse with Pauli matrices. Say delta of A. I'll use this thing, all right? Delta of A square root of the average of this operator squared. So this average is the variance, and the square root of the variance is the standard deviation. The standard deviation of A, usually they write it as delta of A. Just that thing. I'll not put the hat here. So when there is a hat, it's an operator. When there is not, it's just a number. All right? It's better that way. So delta of A, it's just the square root of this thing, and delta of B, without a hat, it's just a number, square root of this other thing, delta of B. And if you take the square root of this equation, you will find that the uncertainty in A, the dispersion in the values of measuring the operator A, multiplied by the dispersion, the standard deviation, or the uncertainty in the values of B, is always greater or at least equal 1/2, if you take the root, the square root there, of the average, the modulus of the average. The square goes away of the commutator. So if you measure B and then you measure A, or in the reverse order, and they do not commute, you'll have an uncertainty related to those measurements. Okay? But of course, if two operators just commute, you will not find uncertainties because you can measure precisely both simultaneously or in any order you choose. But if the operators are incompatible, you need to take care of the order, and this thing, the commutator, is related to uncertainty. So uncertainty principle is related, as a matter of fact, with the representation of physical observables by operators or matrices. All right? This is matrix equation or general equation in Hilbert space. Right? This is the standard deviation of A, this is standard deviation of B given state, and this is always greater or equal to half the average of the commutator. Right? There will be another term here, the anti-commutator, which we dropped out. Right? This is the uncertainty principle. So, as exercises, you can find, suppose for psi is equal to 1/2 up state plus down state here. This is the state. Calculate the average of this, the average of this, the average of that one, and the variances and delta of sigma z, delta of sigma x, and commutators, and show this thing here. It doesn't matter the order now because you're plugging the average and the modulus here. Show this thing here. Okay, you must demonstrate by explicit calculations this is true. Okay, so summarizing, we talked about the uncertainty principle, which is related to operators being physical observables being represented by operators in Hilbert space.